Hello, welcome to this tutorial about LLM distillation. LLM distillation is a method that is gained traction recently. So distillation itself is, a way of training one model to emulate the behavior of another model. And this is a topic that's been around for quite a while, used in like different aspects of machine learning. But recently it started gaining traction in the world of large language models. So Google recently in its Gemma 2 set of models trained them to emulate their larger models using this technique known as LLM distillation. And one of the good things about distillation is that it makes the cost of the training less and enables the model to like learn a lot more from every single example compared to next word prediction, which is the typical approach to training language models, which can be a bit more challenging for small language models and can be quite expensive to train. Distillation is still expensive anyways as well, but it makes the task, a lot easier for small language models, and it's quite more efficient than next word prediction. So in this tutorial, we're going to take a look at like what are the challenges of next word prediction and how does LLM distillation help to fill that gap and, go through some of the maths behind it. So yeah, let's get started. So GPTs are trained via next word prediction, which is that you take an input, in this case like how are you, and you try to predict like I'm fine. So you give the model something like how are you, formatted in the right way by based on like how the model is trained to accept input, and it predicts something like I, and then you take that, concatenate that with the history, and it predicts like You continue doing that, and that's why it's called autoregressive. And what you end up with is these are inputs how are you, and then you give them back uh, the sequence like I'm fine, and this works a lot, and it's led to the most amazing AI innovations we've seen ever, like with GPT-4, Cloud, Gemini, Llama, a whole range of amazing models out there that just keep surprising us every single day with their capabilities. And next word prediction is got its own challenges, right? Because we have like trillions of tokens spread across a whole lot of like sentences, paragraphs, documents, and across all of these, we've got like examples. Like for example, you could find a phrase "When are you coming?" In the training data, and then the job of the model in training is to take "When are you?" and predict coming. But learning from this is inefficient because if you think about it, there are multiple things the model could learn in terms of patterns of like what could come after when are you. So for example, you could have when are you leaving, when are you available, when are you free. And if there was a way by which given this phrase when are you, we could have our model learn all the various patterns of what the completion could be, then that will make the training a lot more efficient, and it's going to reduce the training costs and basically ensure that we can gain more accuracy given a fixed compute budget. Um, because in reality, different words can come after when are you, but in the training data, we can only have like one of these instances at each time. So it makes the training kind of hard, especially for small language models. The bigger the model, kind of the easier the task is. But small language models might struggle with this formulation. And if you think about another example, you could have I'm so excited, I'm so elated, I'm so thrilled. And all of this can occur in nature, but in the training data, only one of these will occur at once. Again, this is like challenging because then we need like to be able to learn all of those patterns, and for a model to work in the real world is going to have to learn a wide range of patterns. To learn more patterns, we are going to have to make up for that by having like more training data, by training for longer. And that's a big challenge because in reality, given sufficient scale, like large model, lots of data, lots of diversity of data, our model will eventually learn all these computations. But of course, that comes like at a much high cost in training models because then we have to like have all these diverse examples. But if there was a way by which from just even one single example, our model could learn all the different possibilities of what that could be, all the different diversity from just one single example. That which is what distillation actually enables us to do, and we'll see that shortly. That will make the task a lot easier, especially for small language models. And first of all, we might think about like why in training, why don't we try to actually train models to have multiple, to be able to learn all the different ways that a sequence can end. And it's because we do not actually annotate each of these data human, right? It's just like we have trillions of tokens, which could translate to like trillions of words, basically, sort of. And at that scale, it's impossible to label the data manually. So what typically then happens is, we are like there's like lots of trillions of tokens collected. There's filtering run upon them to remove like bad data, but the rest of the data is still, as it is, right? Like, the words. If you have like I'm coming in a sentence, it's going to be trained on that I'm coming, and when it's training, the model only learns that formulation, only learns that I'm coming, doesn't really learn all the other ways that sequence could end. So it's again, we go back to that problem of we only learn one thing at a time, which is the one correct token, but we cannot learn all the probable outputs that could come out in a very efficient way. Because human annotation is just impossible at that scale to humanly provide the different possibilities. And knowledge distillation really helps us solve this problem by enabling us have multiple likely targets for every single sequence. So given I am so, instead of just having excited as the singular label, we will basically have a set of possible outputs as the way the completion could end, right? We could have I'm so excited, we could have it as like 0.5, maybe as like the most likely outcome. We could have I'm so elated as a probability set like 0.25 as like it's likely but less likely because I'm so thrilled. So basically we have multiple targets with like different degrees of probability of how that sequence could end, and we are still going to come back to like how these probabilities are actually computed. They are not humanly computed, they're computed by a larger model, because again it's not possible at the scale of trillions of tokens to humanly like assign probabilities. So, but training this way enables us to then like from a single example I'm so learn like three different formulations of that, which significantly reduces the computational cost that we need to reach a certain level of accuracy. So again, these probabilities are computed using larger model. In the case of GEMA 2, they use GEMA 27 billion to compute the probabilities for all the sequences in the training data, and so then train. So that gives us probability for every single sequence, which is impossible to do humanly at that scale. But you could run a model on all of your training data to pre-compute what the probabilities should be, because that model is being trained through next word prediction. So going further, in comparison to next word prediction, uh, start next word prediction just prediction of one thing. So the probability basically for next word prediction is 1.0 for the target, right? It's like I'm so excited, and that's the only thing we know, because we don't know what else is going to happen, right? Because there's no way to intelligently label the probabilities humanly, because the data is at large scale. So we have 1.0 for I'm excited. Compare this to where we have these soft probabilities for multiple targets. In the case of next word prediction, we have one. So in but that's all we can do from large unlabeled trillions of tokens, without having another sort of intelligence pre-computing the probabilities, which is what, pre-trained language models. Once you have a large language model, you can then use that to improve the training data and compute probabilities for your next model, which you want to train, in this case, like a smaller one. And this has like led to like a lot of interesting results, like with gemma 2 they did a number of experiments on a 200 million parameter model, 400 million, 1 billion, by distilling from a 7 billion model. So basically they took a 7 billion model trained via next word prediction, and then used it to compute probabilities on the entire training data, like this sort of probabilities, and then use that and then did knowledge distillation with a 200 million parameter model, 400 million parameter model, 1 billion parameter model, distilled from the probabilities pre-computed by 7 billion. Training from scratch significantly had higher perplexity, and in this case, higher perplexity means worse a result. Lower perplexity means better results. So with distillation, for giving the same the same training data, the same parameter size, we get like lower perplexities, which is a good thing compared to training from scratch with just network prediction, which again demonstrates interestingly like how good network prediction is. How good uh, distillation is. So let's go further. This distillation training process occurs this way. So we got large scale pre-training data, trillions of tokens, and then we pass this to we train a big GPT model via next word prediction on this. So basically standard, nothing fancy, just next word prediction on very large scale data. And that's what we can do, without having a bigger model than the model we're trying to train. So we train a big model on large next word prediction, very large scale data, optimized via next word prediction. Now, once we have that big model, what we do next is we use that model, we run it on all our training data, use it to pre-compute probabilities of on all of the data. So we're going from just next word prediction to then having for every single sequence we have this set of like probabilities of what should come after each word pre-computed as a set of probabilities, which means from every single example we can learn multiple things. So the big model we've trained here is then used to pre-compute that to make the task easier for smaller models to learn from. And the smaller model is then trained via KL divergence, which is basically taking all that training data plus the pre-computed logits. In this case, this pre-computed logits, then using that to train a smaller model that then tries to approximate those logits that then train to behave the same way to have the same logits as the larger model. So we take the logits plus the pre-trained data, pass to the smaller GPT model, and train that via KL divergence. So this is where we move away from next word prediction and actually train the smaller model via KL divergence between its own output and the output of the larger model. So basically, the fact that we already have like a big model trained via next word prediction here gives us that capability, basically trained here, gives us that capability to then do this large scale per token annotation on every single token in our training data, which then makes it possible for us to like train the smaller GPT model in a more efficient way. And now let's take a look at the maths for this, which might provide an intuition for what's really going on behind the scenes. Like, and of course, I've not explained like how does KL divergence work, and we're going to see it here. So in next token prediction, it works via cross entropy loss, where we have an input. In this case, I am so, and the target is truth. So I'm so truth. And we pass I'm so into the GPT model, and we have like a set of output probabilities predicted by the model. The sum of the probabilities is going to be 1. And so we could have excited predicted as 0.3, elated as 0.2, thrilled as 0.15, happy as 0.02, out 0.01. So that doesn't make sense. I'm so out. What does that mean? So very low probability. So basically the total size of this prediction will be equal to the total size of our dictionary, like the dictionary of our LLM. So our LLM can predict one of a total of like 32,000 possible words, which means each time it predicts one of like 32,000 words, that means it's got a vocabulary of 32,000. Then there's going to be like 32,000 probabilities, and you can talk about how big that is. And what we want to do is predict which of those like 32,000 is the most likely, and they're all going to be like based on like some are going to be more likely than others. In this case, excited, elated, thrilled, happy are all more likely than something like house and home, which basically doesn't make sense to do. I'm so well, maybe I'm so home could actually be sensible. I'm so house, maybe not that. We'll say. And so, but in this case, what we're actually trying to predict is truth, and it's got a probability of 0.15. Now remember, let's go back. What we want to do is predict that field to have a probability of 1.0, because that we want our outcome, the actual next token to come to have 100% of the probability, and here we're predicting 0.15, right? So which is like quite low. like actually in this case we are predicting excited. Now this is one of the interesting things about next prediction. Excited might have, is what we predict the most here, but because it's not what is in our label, it's not what is in our sequence, that's not what we want to really predict here. So we, we just take, so the way cross entropy loss is, we take the probability for the correct label, the correct target, which in this case is trilled, and that equals 0.15, and then we compute the negative of the log of that, so which is basically minus log 0.15, and that's going to give us 0.824, which is a high loss, so which means that we need to do better. So basically this loss is going to go down to 0 if our probability, because minus log 1.0 is going to give us 0. So if our probability is like really high, the higher the probability is, the lower the loss. That's it. But the fundamental thing is, in next prediction, the loss is only computed on the correct token, and we try to make sure that the correct token is as high as possible. Now let's contrast this with like distillation loss. Like, so in distillation, in this case, we use KL divergence, and the way KL divergence works is by computing a sort of a distance between the predicted distribution of outputs and the target distribution. So let's think about it this way. You have I am so, and if we took a bigger model, use it to pre-compute the probabilities of what should be next by running it on that sequence and computing the probabilities outputted by the bigger model. So we could have maybe excited at 0.2, elated at 0.25, thrilled at 0.5. So we got this as our, in some sense, GT probabilities. That's basically the behavior, because we want to emulate the behavior of the bigger model. So we're going to use the bigger model to pre-compute that. We call that T, in this case, indicating target. And so that's our training data, right? And then this set of probabilities. Now, what we then are going to do is, in training, we are going to pass to the smaller GPT model. It's going to predict its own output, which is, at the beginning, especially, it's not going to be the same as the target. So let's say for our smaller GPT model predicts 0.3, excited at 0.3, predicts elated at 0.2, and trilled at 0.15, which is basically the same thing we had here, right? And so let's say predicted this, and we could take the top three, right? We have like top three, we have top three probabilities predicted by the big model, and then we could take the top three predicted by the small model, and we compute a divergence between those two, basically between this and this, because we want this to be exactly equal to this, because we want this excited to be 0.2, we want elated to be 0.25, we want trilled, which is 0.15, to be 0.5. So that's basically what we want to do. We want the smaller model to approximate the behavior of the bigger model. And going further, the way this works is that we got these two, this T probabilities, which is the target distribution, this P, which is the predicted distribution from the small model, and the KL divergence tries to measure divergence between T and P. Given T here, P here, KL divergence is basically computed as, the sum of the target probability multiplied by the log of the target probability divided by the predicted probability. So Ti being one of these, in this case 0.2 is Ti, T0, where I could be 0, 1, 2. So in this case T0 is 0.2, P0 is 0.3, and so this is going to be like 0.2 divided by 0.3 here, and then this will be 0.2, and then once compute a sum, we do that for this, do that for this, do this, do that for this, and then compute a sum. So basically we're computing the divergence between these two T and P distributions. So let's look at how to actually compute that. It's very simple. First of all, we normalize the vectors. We want the vectors to all sum to 1. So basically the way we do that is we take each of it, like in this case for T, we have 0.2, right? We have 0.25, we have 0.5, we add them together. When we add them, we have 0.95. So that's 0.2 divided by 0.95, and then 0.25 divided by 0.95, and the rest. And then that gives us this 0.2105, 0.2632, 0.5263 as the normalized vectors. We do the same for P. We normalize it to sum to 1. Basically take the sum and divide each one by the sum, and then we have got this. So now the KL divergence becomes, find the KL divergence between these two normalized vectors. And we're going to do that in the next slide. So what we then do here is just simple, right? We take t, which is now, this normalized output, and we do 0.2105 multiplied by log of 0.2105 divided by this plus this 0.2632 multiplied by log of 0.2632 divided by 0.307. Then we do this for the truth as well, right? Basically, we just compute that, which is this equation, and that gives us a total of 0.2275. So that is then the KL divergence between these two distributions, and we want that to be as small as possible, right? We want basically the divergence to go to zero. In practice, of course, the divergence will never go to zero, but we want it to be as low as possible. And by training the model this way, where we've gone from just computing this loss function, this one, which is a very simple loss, and that's how the big model is going to be trained. And it may, given sufficient compute, sufficient big model, sufficient data, it works. But for smaller language models, it's going to be a lot more efficient if we just use the big model to pre-compute probabilities like this, and then train the small model to approximate those probabilities by doing a KL divergence between these two. And the step to do that is, normalizing it, and then computing a KL divergence between the two normalized vectors, and then getting this value, which we then minimize. So that's basically what I wanted to explain today, and it's this will really interesting way of taking large language models, small language models, training them, which is quite an exciting thing to do. And it's very expensive, but if we already have a big model that has been trained, in this case, take like Llama 4 or 5 billion, you could use it to, imagine distilling it 5 billion, 4 billion, maybe 2 billion parameter model from Llama 4 or 5 billion by using Llama 4 or 5 to pre-compute probabilities on the entire training sequence, and then training a 2 billion parameter model to approximate that distribution. And at each single step, it's able to learn so many things because we have like multiple outputs. We are not limited to just using top 3, you could use like top 10 or whatever. But basically, the most, it could be like top 5, the most likely outcomes, and training a small model to do that rather than, and this is a lot more efficient than taking the small model and doing next word prediction on the entire training data. So yeah, this has been quite exciting to follow up with this, how it's been evolving, and I'm really expecting to see more models, especially small models, trained this way going forward. Thanks a lot for listening to this tutorial. I hope to make another one soon. Yeah, until then, thank you.